Welcome to my world. What you're looking at is a Linux desktop application written in C that I've been working on for almost exactly a year now. The purpose of the app is to simulate the operation of a 1960s vintage computer called an IBM1620, which was in common use during that period. I call my app Neo 1620, or Neo for short. Running a real 1620 a half century ago was a hands-on experience, requiring an operator for such things as setting program switches, loading card decks, mounting disk packs, entering instructions on the console typewriter, and many other things besides those. Neo simulates these actions by the use of a PC keyboard and a console, which is rendered by a graphics package for Linux called GTK. The input-output devices of Neo are virtual. They are Linux text files. So when I/O operations are performed involving the card reader, the card punch, the printer, the paper tape reader and punch, those are all actually I/O operations directed either to or from Linux text files. One of the objectives of my Neo application is to emulate the complete 1620 instruction set. Now, whether that goal will be completely fulfilled, we will see. Right now, 35 out of a possible 69 opcodes are already supported. We're more than halfway done. The next one being designed is opcode 23 for multiply. A real 1620 had a maximum memory range of 60K. Neo extends that to 100K. 1620 console keys like insert, release, and start are simulated on Neo using PF keys. The console of Neo was inspired by a 1620 Model 2 console, which is less complex than the Model 1 console. Neo's console appearance doesn't replicate the real Model 2 console, but tries to at least have a family resemblance to it. Console indicators and switches are situated in locations relative to each other, which are hopefully familiar to those with 1620 experience. The labels for console indicators use short abbreviations because of desktop space limitations. For example, last card is LCD, carry in is CRI, branch exec is BRX, and so forth. Console indicators are not bulbs, either lighted or not. Instead, an indicator in an off state is shown as a dot, while the on state is shown as a capital letter O. Let's talk about Neo's console some more. I'll first start Neo up so I can show you things instead of just tell you about them. The console appearance right now is what you see when the Neo application is first launched. Neo hasn't been turned on yet, so it's in what I would call the nascent state. I'll talk more about the master output window in the lower right later, but right now you will notice that it's prompting the user to turn Neo on using the power key PF1. So let's press it. A few seconds after the power indicator lights up, the ready light comes on, and Neo is ready for business. Neo's console has everything a real Model 2 console does, with some extensions. One extension is that in the upper right, instead of a rotary MAR selector switch, there's a linear selector action by PF12, like this. You could press PF5 to display MAR for any of these registers, but right now they're all zeros, so it's not really going to show you anything. The program switches are shown in the center of the dark blue section. The question naturally arises, well, how do you turn these program switches on and off? Neo simulates physical operation using scripts, which are just Linux text files. There are two scripts Neo uses, the user script and the master script. The user script is where a user codes script commands to turn switches on, load 1620 programs, start execution at a certain core memory address, and other actions. The user script is coded to set up Neo to run a job, and then the Neo application is launched, which runs the user script automatically. I can't demonstrate this yet, it's not yet finished. The master script is part of Neo's supervisor program, which I'll call master. Master is what controls the operation of the Neo app. The master script is where the code is for emulating 1620 instructions and running 1620 programs. The master script is always running in Neo unless something unusual has happened, like a user's 1620 program has caused a check stop. Right now, Neo doesn't look like it's doing anything, but the master script is alive and waiting for work to do, which is emulating a user's 1620 program. Let's show you what I mean. Neo's master script is a big text file, nearly 6,000 lines long. It's running at this moment, even though Neo is idling. To show this, I'm going to use a feature called IMM, or Interactive Master Mode, to execute a single script command entered on the console. To enter the IMM command, I'll press the escape key. When I do that, you'll notice that a console indicator labeled IMM near the middle of the dark blue area will light up, and just to the right of that, you'll see a blinking prompt showing that Neo is expecting to be given a command. So let's hit escape. You'll see the prompt in the master input area. The command I'm going to give it turns on a special feature bit to display a master script trace. This command is called a set. So let's type that in. In the master output window, it says that the return code for that command is 0, so that worked. Let's now enter a command called can, or cancel, which cancels interactive master mode. Right now the master script is active but paused until our IMM session is finished. So let's enter can. When we cancel IMM, we can see in the master output window the trace of the master script as it idles, waiting for work to do. It's in a fairly small loop. You can see it repeating the same commands over and over. The trace would look very different if there was a 1620 program being executed with emulated 1620 instructions, but Neo hasn't been told to do that, so it just idles. Neo is to a large extent just a script engine running the master script that never or hardly ever stops, waiting for some real work to do. If we were to use 1620 insert to enter instructions to emulate using the console typewriter, the master script would know this and start emulating those instructions. Let's show what that looks like. Before going farther, let's turn off the master script trace by turning off that feature bit we set to 1 earlier. I'll press escape again for IMM. To turn off the feature bit, I'll use a set command again, but I don't have to type it in this time. That's because Neo maintains a command history. I just press home a couple of times to retrieve the set command I entered earlier and we'll modify it. So I'll hit backspace, change the value that we'll be setting to a 0, hit enter, and that looks like it worked. Now we'll issue the cancel command again, but once again, I don't have to type it. That's in the command history, so I'll just hit home a couple of times, and there it is. I'll press enter, and the cancel worked, and we're back where we started. The master script is running again, but the master script trace has been turned off. Now I can demonstrate how to enter a short 1620 program using insert and run it under Neo emulation. Neo is in manual mode right now since nothing is being emulated. By the way, there's a console indicator labeled EMU in the upper left that shows this. There it is. And the EMU light right now is off. We're about to change that. In manual mode, we can press the insert key, PF7, and when I do that, there's a console indicator labeled INS for insert that turns on, and a blinking cursor just to the right of that in the typewriter input window indicates that Neo is awaiting console input. Let's enter a little program to decrement a small counter and dump that into the typewriter output window, then carriage return and repeat until the counter is 0, then halt. So let's type in that program. Transmit field immediate, 16. We're going to use the very top of memory, all 9s. K00 is flag 200. Next is the subtract immediate, 12 to our counter. And we're going to subtract a value of 1. So that's what that looks like. The right bracket is a flag 0. Then we'll do the dump instruction, 35. It'll be 3 digits that we actually dump before it stops automatically. 00100. Then we'll do a carriage return. Then we'll do a branch on the high positive indicator back to the subtract immediate. So we'll do that with 46 to 12, and high positive is 01100. And when the counter is no longer positive, it will fall through to a 48. So when we press enter, we'll see how this runs. And away it goes. Doesn't take very long, 200 iterations of that loop. We see that the EMU light is still on, even though the program has finished. That's because the halt that we're using here, we can see the 48 in the operation register. The type of halt we're using does not exit emulation. That's done with a special halt instruction with a P address of all 4s. If you do that, then it will Neo will get out of emulation mode and go back to manual mode. But this type of halt is just a simple halt in a user program. If we had had a branch following this halt, say back to the start of the program, it would repeat. But right now I did not do that. But this is how entering a short program on the console and running it looks like. Now, veterans of the 1620 will observe that the typewriter dump loop is much faster than a real 1620 could ever hope to do it. I didn't make it this way on purpose. This is just how quick Neo runs. If we do insert, release, and start, we can see that run again. Insert. We can either do PF8 for release and press PF9 for start, or we can just press the enter key. I'll just do it the easy way. Pretty quick. Now let's run the same little program, but this time we'll step through it using single instruction execution and single cycle execution. Our program, of course, is still in low course, so all we have to do is press insert, release, and start to repeat it. But instead of pressing start this time, we'll press PF10 for SIE mode. By the way, in another example of console function extension, there's a new console indicator for both SIE mode and SCE mode in the upper left. And that's where those are right there. So let's press insert, release, and PF10. And you'll notice an acknowledgement there in the typewriter output area of the key sequence that I just entered. And we've continued to press PF10, and we can see that it's stepping through our program one instruction at a time. Okay, that's what SIE mode looks like. We see that the SIE mode indicator is lit over there. Let's instead go into SCE mode by pressing PF11 instead and see what this looks like. Okay, when we do that, we can see that it's stepping through the I cycles and E cycles of each instruction. When we get to the dump, the 35 opcode, we'll see that for every press of the SCE key, he's outputting one digit and showing its address in MAR and displaying the digit in either MBRE or MBRO, depending on whether the digit comes from an even address or an odd address. Let's do the 35 again. There it is. He dumps 3 digits and stops. All right, let's press PF9 and let this thing finish. Running small programs on Neo by typing them in is fun, but what about programs that are medium size or large? There are several ways to load and execute sizable programs on Neo. One day I hope to be able to run the Monitor operating system and run programs conveniently that way, but until Neo is able to use Monitor, there are IMM commands that can be used for this purpose. These commands work together with Neo's virtual I/O devices. When Neo is launched, the virtual devices are assigned so as to point to Linux text files. The IMM commands I'll be demonstrating are designed to use particular virtual devices to read a program into 1620 memory and execute it under emulation. I'll first show how to use iDevice5, the card reader, to load and execute a program. If we take a look at the terminal instance messages, when Neo was launched, we'll see the virtual I/O devices and how they were set up, and we see that iDevice5 has been set up to point to a .crd file. This file is an executable, and it was created by IBM1620, the assembler designed by a new friend I've made during the last year named Dave Babcock. Using Dave's assembler, I've designed a Neo test program for add, subtract, and compare. The IMM command CEXE is designed to read and execute executables like this. Here's what CEXE looks like when I run my test program on Neo. First, I'll get into IMM by pressing Escape. There's the prompt. Now I'll type the command CEXE and press enter. And when I do that, some messages will briefly flash across the output windows, but it will show you that the program is being read and executed. Let's see how that looks. There we go. The first thing that my test program does is issue a message to type output, and it shows there. So it's prompting me to press PF9 to start, and so this is what happens after I do that. The program runs to completion normally, so that's how that looks when you use CEXE to run a program that is a .crd executable. Another way to load and execute a 1620 program is to use the IMM command cmemx while the virtual input device IDevice6 is pointing to a .cmem file, which SPS1620 can also create when told to do so during an assembly. IDevice6 is an extension of 1620 I/O for using stream input. Stream input is similar to card input, except there's no restrictions about line lengths in the input file the way there would be for a card file with the 80 character limit for lines. Stream input lines are variable length and can be up to 300 characters long. Here's what cmemx looks like to load and run the same test program I ran before. By the way, IDevice6 can be used directly by 1620 opcodes 36 and 37, which specify the 2-digit device code 06 in Q8, Q9. So let's execute cmemx and show you what that looks like. We'll get into IMM, type in the cmemx command, and we will tell it that the execution begins at this address. When we press enter, it will take off. And it looks kind of like it did before. The first thing it does is issue that message prompting us to press start, so we do, and the program runs to completion. Yet another way to load and execute a 1620 program is to use the IMM command CINX, which uses iDevice5, the virtual card reader, in a different way than we used it before. Earlier I showed how to use the CEXE command with iDevice5, but it had been set up to point to a .crd file, which is a different type of file than the one we will use now with CINX. Just before recording this segment, I relaunched Neo while assigning iDevice5 to a file with a file extension of .cin, which means an image file of 1620 numerics. The CIN file that CINX reads is a numeric image file using an 80 position card structure. This CIN file is essentially a core dump of a 96K digit benchmark program I use for Neo, which has an assortment of 10 types of instructions repeated 600 times. I designed the program this way so that it would exercise nearly the total 100K memory range. I created the big CIN file by getting the 96K program into memory, and then I inserted and executed 5 opcode 35 dump instructions using odevice4, the card punch. Opcode 35 will only output a maximum of 20K digits at a time, so I had to write 5 separate card punch files and then splice them together end to end. The way Neo handles virtual device files, there are basically two types of these, image files and what I choose to call package files. Image files, either alphanumeric or numeric, have a one-for-one relationship between the ASCII characters representing data and the actual data as it will reside in 1620 memory once it gets there. To read and load an image file, all a program has to do is read into an address, increment the address, and then repeat until the end of the file. Very simple-minded. To read and load and execute a package file, a more intelligent kind of loader has to be used, which acts differently based upon the data being read. A package file does not show a one-for-one relationship between the ASCII characters representing data and the data itself for the entire file. A package file has what you might say is intelligence embedded within it, along with the program data. Now let's get into IMM and show you what the CINX command looks like when it executes a .cin file. So we hit escape, we type in CINX and the starting address and press enter, and it's done. 8001 instructions. The final thing I'm going to show in this first Neo 1620 video are what Neo shutdown, an orderly shutdown, looks like, and then I'm going to show you some of the artifacts created by the Neo application when it runs. Let's shut Neo down. There is an option that I can use that will allow me to pause a number of seconds and study the messages that are produced during shutdown before everything goes away. I think I'll use that this time. So let's go into IMM and type the command stop with let's say 30 seconds, and let's show what that looks like. Let's expand this so we can see everything that it did. And we have basically 30 seconds to study these messages and decide if we like what we see, if you're the programmer like me, and if not, there's something to fix. Within a few seconds, the GTK display of the console will disappear automatically, and you'll see some messages, there we go, saying that we're finally winding up, and we're gone. Let's go into the home directory and let's look for some artifacts of the run we just made. And there they are, right here and right here. There is a copy of everything that went to the master output window, and we open that. There it is. Not really a lot. We did the CINX command in this last session, and we did an orderly shutdown. We really didn't have any typewriter output for this very last segment. I can tell that because I thought this was an artifact of the last run, but it's not, because the timestamp is different. There's the date there, and the times are different between these two. But here is what the typewriter output window contained in the previous run, and that was one of our arithmetic tests that I showed you. So when a run ends for Neo, you can go back and find artifacts of what happened and perhaps that would be helpful to a lot of people. So that's why I designed it to be like this and keep these files out here. Any output files that are empty are deleted automatically. Well, I hope this has been an interesting video for you. I'll get back to work now, either on the design of support for another 1620 instruction or support for address indexing, which I'm kind of dreading, but it should be interesting in its own right. Thanks for watching, and all comments are welcome.